This video is going to talk about the power rule for derivatives. Before we do that though, let's talk about different ways you might see the derivative written. The first way you might see is what we call the Leibniz notation. And in Leibniz notation is another way to write f prime of x, the derivative. If you're normally thinking of y equals f of x, right, then f prime of x would be the derivative of that. But the other way you would see it is written as dy over dx. Doesn't mean divide. What it really means is take the derivative of y with respect to x. That's how you would read that. All right, so take the derivative of y with respect to x. All right, so that's one way you might see it. So that's the Leibniz notation. The other ways you might see it, right? So the derivative of y equals f of x can be written in the following ways. So you might see it as f prime of x, which we're familiar with from previous section. The Leibniz notation I wrote above, dy dx. You might just see it called y prime. Right? It means the derivative of y, which is y prime, saying f prime of x for that function. Or you might see it written like this, d dx of f of x. That means take the derivative of f of x with respect to x. So these are different ways, all mean take the derivative, right? So you should have an understanding of that. Sometimes they might give you the derivative and they're just asking you to substitute in, right? If I said something like this, for example, if I said given f prime of x equals 3x squared minus 5, find f prime of 6. Well, remember, f prime of x is also a function, right? So when I say f prime of x, a function of x, 6 is the x value they want me to substitute in. So all I'm doing is subbing in. So this would be f prime of 6, which is equal to 3 times 6 squared minus 5. Make sure you're following your order of operations. This would be 3 times 36 minus 5, which ends up being 108 minus 5, which equals 103. So if they give you the derivative and they're asking you to substitute in, this is one way they might ask you to do that. You might also see it in the Leibniz notation. If I said, for example, given dy over dx equals x squared plus 4x minus 6, find dy dx, and they put this bar next to it and they put this condition, so x equals 2. So this really is the Leibniz notation. It's saying this is y prime, this is the derivative, and they're saying the derivative of y with respect to x is equal to this, right? So the first derivative is equal to that, and it's saying find dy dx when x equals 2. So all it's saying is the same thing what we said above in terms of this is telling you to substitute in x equals 2 into here and evaluate. So this would end up equaling, right? So dy dx for when x equals 2 is really just equaling, subbing in, you would have 2 squared plus 4 times 2 minus 6. And then, follow your order of operations, evaluating this, we end up with 2 squared gives us 4, plus 4 times 2 is plus 8 minus 6. 4 plus 8 is 12 minus 6. This just equals 6. So if they give you the derivative and they ask you to evaluate, these are ways you might see it. But just so you have that information before we go forward in the course, because these are going to be things that you're going to use within problems, within different problems we give you. So let's talk about the power rule. So this is a rule on taking derivatives. Now previously we learned how to take derivatives using just the limit of the difference quotient. Now and from any point forward after this section that we're covering in the course, we'll have shortcut rules to find the derivatives. I'm not going to prove why they work, but they come from that limit of the difference quotient. So the first rule we have is what they call the power rule. Alright, so the power rule says for any real number k, the derivative, right? So derivative with respect to x, that's what d over dx means. So the derivative with respect to x of x to the k power is equal to, and what it really tells you to do is you're going to take k and put it in front, so you'd be k times x, and then you subtract 1 from the power, so x to the k minus 1, and that's the rule for how you find the derivative. Remember, this is telling you something to do. The d over dx is saying take the derivative of this with respect to x. You don't write d over dx in over here. So what it's really saying is that if you have, some variable raised to a power, to take the derivative of it, you bring the power out in front and then you subtract 1 from that exponent. So let's take a look at some examples. So if I said to differentiate, remember differentiate means take the derivative. All right, so differentiate each of the following. And let's take a look at this first one. If I said I had y equals x to the 6th power. Well, if I'm taking the derivative of this, the derivative of y, make sure you understand this, will be called y prime. And it's equal to, how do you take the derivative of a base x to a power, right? Some variable to a power. What's the rule say to do? It says take that 6, bring it to the front, so that's k, right? So 6x to the, subtract 1 from the power, 6 minus 1 would be 5. So y prime is equal to 6x to the 5th. So basically you bring the power in front and subtract 1 from that exponent. And then you have it. Right? There's really not anything else to do with that. What if I wrote this one? If I said f of x equals x to the negative 8 power. Again, we have x, right, being raised to a power. If I'm trying to take the derivative, so the derivative of f we call f prime of x. Make sure you write that. Right? So f prime of x is equal to, taking the derivative, it's a variable raised to a power. You bring the power out in front, so negative 8 in front. And this is x to, remember, you're subtracting 1 from the power, so negative 8 minus 1 would be negative 9. Right? Negative 8 minus 1 is how you get there. It's negative 9. And you could leave it like that. A lot of times we're going to simplify these. If you wanted to simplify this, negative 8 times x to the negative 9. Remember, the negative 9 on the x is the exponent only on the x, not on the 8. So the negative 8 will stay where it is. The negative exponent on the variable tells you to move it to the denominator and make the power positive. So it's negative 8 over x to the 9. If I ask you to not simplify, sometimes I'll put in the directions do not simplify. I want you to leave it like that. If I ask you to simplify, I'm asking you to rewrite it in the most simplified form, meaning that we can't have any negative exponents in our final answer. But a fairly easy concept, I think. It's more about knowing the algebra when you simplify after. What if I said this? If I had y equals just x. Well, we're asked to differentiate, so we're trying to find the derivative. The derivative here would be y prime, and that's how you write it. Equals, now, how do you take the derivative of x to a power? What's the power on this x? Well, the power on this x is really 1, you just don't see it. And what do? You bring the 1 in front. You have 1 times x to the 1 minus 1 power, which is 0. Well, what's x to the 0 power? Right? Because remember, the 1 is still here. This is 1 times x to the 0 would be 1. So this whole thing equals just 1. So we have y prime equals 1 here. So if you're ever taking the derivative of x to the first power, or a variable to the first power, when you take the derivative of that, right, it just goes to 1, because really the x to the 0 just becomes 1, right? Anything to the 0 power equals 1. That's a rule that we should know. You don't really have to show work for this. If you know derivative of x equals 1, you just write it. And how about if we look at this one here? If I said I had g of x equals x to the 1/3 power. Well, this is a base to a power. Don't think that the power k has to be a whole number, right? The directions or the rule says for any real number k. So it could be a fraction, could be a decimal, could be a whole number or an integer. But in this case, I'm looking for the derivative. Make sure you know it's called g prime of x. Call it by the correct label, right? So g prime of x equals, well, how does the rule work? If I have a variable to a power, you bring that power down in front. So it's 1/3 x to the, remember what I do, I subtract 1 from the power. So what's 1/3 minus 1? Well, 1/3 minus 1, in case you're not sure, this ends up being negative 2/3 is the power. You would need a common denominator. 1/3 minus 1 is the same as 3/3. Remember how you can rewrite that over 3. 1 minus 3 gives you negative 2 over 3. That's how we're getting that power. This is just a little aside in case you forgot. Once you have this, you know, if I don't ask you to simplify, you could leave it like that. That's perfectly good. If you wanted to simplify this, remember the negative exponent on the x is telling you to move it to the denominator. Okay, right, this is 1 over 3. The x moves down to the denominator. The power becomes positive, so the x to the 2/3. And you could write it as g prime of x equals 1 over 3 x to the 2/3. You could also talk about how that 2/3 changes our exponent as well, in terms of, you know, if you have a rational exponent, that will be a radical, really. And we'll talk about that more in the next examples, but just making sure you have an understanding of the rule for this part. So now there's some examples that might be unique. They're a little different, right? So the other ones, I didn't really have to do any manipulation at the beginning. The problem was already a base to a power, or I should say a variable to a power. So in these next ones, we'll still have the same rule apply, but we'll talk about how you have to kind of manipulate them first. So if I said, right, differentiate. All right, so it might say differentiate, might say take the derivative, might say find f prime of x or whatever variable they're looking at. But if I say differentiate, if I said I had y equals, we'll call this the 3rd root of x to the 4th, you know, this really isn't following the actual, you know, rule I had, right? The power rule said it had to be x to a power. Right now that's not written as x to a power because I have this cubed root around it, right? So even though the x to the 4th is on the inside, that cubed root around it changes what the power is. So the first thing you want to do, and this is important, is that you want to rewrite. And I'll use RW for rewrite when I do this. A lot of what we do in this course, and a lot of what you do in math in general, is rewriting into a different form, an equivalent form, that makes it easier to work with. So I'm going to rewrite this as y equals, don't put y prime because I'm not taking the derivative yet. I'm just rewriting it into a form I need. So I want to rewrite this as x to some power. Well, how do I rewrite this? The cubed root of x to the 4th. Remember how it works. The power goes in the numerator. The root goes in the denominator. The roots are in the bottom like a tree. So we make a rational exponent on it. The root always goes in the bottom, right? So the index of the root is 3, so it goes in the denominator there. Now once you have this, now we're ready to take the derivative, because now I have the form I need to use the power rule. So the power rule says that y prime, the derivative, is now equal to, bring the power down in front, right? The whole thing, the whole 4/3. So 4/3 comes to the front. We have x to the, now subtract 1 from this, 4/3 minus 1, well it's 4/3 minus 3/3, so it gives us 1/3. If you're not sure how to subtract 1 from this, right, really, it's always whatever the denominator was, and then subtract over the denominator from the numerator and keep the denominator the same. So we have x to the 1/3 there. And, you know, if I said do not simplify, you could leave it like that. If I asked you to simplify, let's rewrite this. Y prime is equal to, this is 4/3. x to the 1/3. Well, how do you write that as a root? Well, the power on the x is 1. The root is 3, so it'll be the cubed root of x to the first power. So y prime is equal to 4/3 times the cubed root of x. And that would be your answer. Having an understanding of those rules for the rational exponents is really important here. It'll come into play throughout the entire course. Let's try another one. If I said I had f of x equals the square root of x. Well, again, I don't have a form I need, so first thing I want to do is rewrite this. Remember, you're not taking the derivative. It's the same function, f of x, just rewritten in an equivalent form. Well, how do I write the square root of x as x to a power? Well, it's x to the, remember, it's a rational exponent if you see a root in here. The power on the x was 1, so 1's in the numerator. The root, the index is, the square root is 2. Make sure you put that there, right? Just because you don't see anything doesn't automatically make it a 1, right? For square root, it's really a 2. All right, the power on the x was a 1. So we have f of x equals x to the 1/2, and now I'm ready to take the derivative. So now I'll write the next part as f prime of x. The notation's important. Don't be sloppy here. You want to make sure you're clear with which part is which. One's a rewrite, one's the actual derivative. So f prime of x is equal to, the power rule says bring the 1/2 to the front, so you'll have 1/2 x to the 1/2 minus 1 power, which is negative 1/2 power. Right, so 1/2 minus 1 is going to be negative 1/2 is the exponent. Now, if I don't ask you to simplify, if I say do not simplify, leave your answer in this form. But because I want to show you how to simplify, and this is where your algebra skills come into play, you have 1/2, you have x to the negative 1/2. Remember, the exponent's only acting on the x, not the 1/2. The negative tells you that it should move to the denominator to make the exponent positive. So you have 1/2, and now we have x to the positive 1/2. And then think about how you can rewrite that. The 1/2, if you see a rational exponent, it tells you can write it as a root. So this is going to be f prime of x equals 1/2, and then x to the 1/2. Remember, the denominator tells you about the root, so it's the square root of x to the first power, so the square root of x. And that would be the simplified form. Let's look at this one here. If I said I had y equals 1/x to the 5th. First thing, you can't just write this as 1 and then do the power rule on the denominator. It doesn't work like that. Remember, the power rule is for the variable raised to a power. Right now, this is not that form because we have a 1 over that. But how could I write this in an equivalent form? Well, the rewrite on this, how do I get variables out of the denominator? In other words, into the numerator. How could I write this as just x to a power? The key to this is making sure you remember the rule that says if you have x to the negative n power, that's equal to 1/x to the n. We're really going to use this rule in the opposite order. We're going to say take the 1/x to the n, you can write it as x to the negative power, and that's how you'd move it up. It's kind of undoing the rule that we did here, right? This x to the negative power told us to move it to the denominator. We're trying to move this back up. You want to make that to the negative power. So I have y equals 1/x to the 5th. The rewrite, now remember, rewrite is an equivalent form. So keep it as y equals. Don't put the y prime in that. It's x to the negative 5. If the 1 was a different value, like let's say it was a 4, you would write it as 4x to the negative 5. The constant would still stay there in the numerator. Now once you're at this point, you can take the derivative as we had before, because now I have a variable raised to a power. So now I can find y prime. Alright, so the derivative of x to the negative 5, so you take negative 5, bring it in front, and then we get x to the, remember you're subtracting 1, negative 5 minus 1 is a negative 6. Make sure you're careful with your negatives, right? Negative 5 minus 1 makes it more negative, so it's negative 6. And if I didn't ask you to simplify, you could leave it like that. To simplify this one, y prime equals, now negative 5x to the negative 6. Remember, the negative 6 is the power on the x, not on the negative 5. So the negative 5 stays in the numerator. The negative 6 is telling you to move the x to the denominator and make the power positive. So we have negative 5 over x to the positive 6. And that's a simplified form. If I say do not simplify, you can leave the first form. And maybe we'll look at one more like this. If I said take the derivative of g of x equals 1 over the square root of x cubed. So again, I want to try to rewrite this as x to a power, right? Right now it's not x to a power. So the rewrite on this, right, if you're thinking about what it should look like, it's still called g of x because that's the name of our function. Don't put g prime, we're not taking the derivative yet. This is rewriting it in an equivalent form. Well, what is this equal to? Well, the base, we know we want it to be x. To move it up to the numerator, we know it has to be negative. Let's talk about how you rewrite the root and the power here, right? So the power is 3, so we know it's going to go in the numerator. The root is a square root, so it's going to be over 2. So it's x to the negative 3 halves. You should know how to rewrite this. All right, so x is the base. The power becomes negative because you're moving it up to the top. Power on the x was 3, so that's the numerator over the index of the root, which was 2 because it's the square root. Once you've rewritten that, right, and if you have to, you could do this in 2 steps, right? You could say this is 1 over x to the 3 halves, and then no, you have to move it up as x to the negative 3 halves. Sometimes people need that intermediate step, and that's okay if you do. But make sure you remember, it's all equivalent to the original function. I haven't taken the derivative yet. So now, I'll take the derivative, g prime of x. The derivative says, right, if you have a variable to a power, you bring that power down in front. So you have negative 3 halves, x to the, now remember, you're subtracting 1, negative 3 halves minus 1 is negative 5 halves. And if I tell you not to simplify, if I say do not simplify, you can leave it like that. If I ask you to simplify g prime of x, remember we want only positive exponents in our final answer. You can write this as negative 3 is in the numerator. The x to the negative 5 halves tells you it's going to move down to the denominator and make the power positive. So I have negative 3 over 2. And then this will be x to the 5 halves. And I'd be okay if you kind of, you know, left this for now. But knowing how to simplify this is somewhat important. You could simplify this as this is negative 3 over 2. Now, if I say x to the 5 halves, that's the same as saying what? The square root, because that's your denominator, is 2 is the index, the square root of x to the 5th. And you should know how to simplify the square root of x to the 5th. This is negative 3 over 2. The square root of x to the 5th, you can really think of it as the square root of x to the 4th times x, because remember how this works. An even power is a perfect square for a variable, so the square root of x to the 4th would just give you x squared, and you have a square root of x left over. So it's important to know how to simplify this. If you left it like this, I'd probably give you full credit, because later on, you know, we'll use these in different ways. But it's important to understand that this is how you simplify your answer. Let's take a look at the derivative of a constant. So the ones we've done so far have all been power rule with variables. We're going to look at the derivative of a constant just to make sure you know what to do with it. It's actually the easiest rule we have, but sometimes people forget it. So the derivative of a constant. All right, so the derivative of a constant, for any constant, which I'll call C, the derivative of x, right? So, or I should say the derivative with respect to x of C equals 0. So you take the derivative of a constant, it's always going to be 0. So let's take a look. All right, so we'll do some examples of this. So I'll say differentiate. If I said y equals 6, well, what's the derivative? Y prime. 6 is a constant, right? There are no variables there. So the derivative of a constant always equals 0. So y prime equals 0. Now, the reason this is true is think about what the derivative represents. It represents the slope right, at a point, right, for the tangent line. So it's a slope at a point on the original function. Well, if it's a constant, the original function is just a horizontal line. So what's the slope of a horizontal line? Well, the slope of a horizontal line is 0. So that's one way you can think of the derivative of a constant being 0. So y prime equals 0 there. You know, you could have something like this. You know, f of x equals negative 135. Well, what's a derivative? What's f prime of x? Well, there are no variables in here. So, right, that's like y equals negative 135. The derivative of that, all right, derivative of a constant, always 0. Don't let it throw you off if the constant is something that doesn't look like a number you're used to seeing. Like if I said y equals pi. Remember, pi is a number, right? It's an irrational constant, but it's still a constant. So what's the derivative? Well, the derivative of a constant is 0. So y prime equals 0. And just do one more. If I said, you know, g of x equals the square root of 7. Well, what's the derivative here? Well, square root of 7 is a constant. It's, you know, it's an irrational constant, but it's a constant. So g prime of x equals the square root of a constant. Or I said g prime of x, the derivative of a constant, sorry, is 0. What you don't want to do is you don't want to rewrite this as 7 to the 1/2 power and then bring the 1/2 down and then subtract it from the exponent, because it's all a constant. It doesn't follow our power rule, right? Our power rule was for x to a power, right? The variable to a power. If it's a constant to a power, you wouldn't do anything. It's still a constant. Derivative of a constant gives you 0. Let's talk about this next part, is the derivative of a constant times a function. Right, so the derivative of a constant times a function. So if I said I had the derivative, I'll call it d over dx, right? So the derivative with respect to x of c times f of x, right? So a constant times a function. So a number in front of a function, in other words, right? A number that you can see in front of a function, something with variables. It's equal to, what you really can do is you can bring the constant to the front. So you can write it as the constant times, and then just take the derivative of the function. Right, so derivative with respect to x of f of x. This is really saying that it's kind of like our limit rules. If you have a constant in front, you just keep the constant in front. You take the derivative of just the function part. And these are equivalent. So you don't just make it 0, right? These ones didn't have a variable piece. These were all constants. That's why they became 0. But if you have a constant times a function, it's not just a constant. It has a variable part. You have to use the rules that we've talked about. So let's take a look at a few examples. If I said to evaluate and the first one I'll say is d over dx of 5x to the 9th. What you really do here, all right, the derivative with respect to x of 5x to the 9th. This is a constant in front, so you put 5 in front, and then you multiply by the derivative of the function part of the x to the 9th. So we'll do this just right next to each other. I'm not going to write the formal notation. So it's 5, the constant in front, times the derivative of x to the 9th. Well, how do you find that derivative? You bring the 9 down, and then make this x to the 9 minus 1 power, which would be x to the 8th. And then simplifying that, 5 times 9 would give you 45x to the 8th. So the way people normally look at this is they really just say, okay, 9 times the 5 in front, and make it just 45x to the 8th. And that's the answer for the derivative, right? So we've taken the derivative there. You don't have to write the ddx anymore. Remember, that was only because that's giving you instructions on taking the derivative. If I wrote this one, take the derivative with respect to x for 3x to the negative 8. So what do we do with this? Well, it's the same idea, right? The constant 3 is in front of the function, so the 3 would stay in front, and then you're just going to take the derivative of the function piece. The derivative of the function would say, okay, bring the negative 8 down in front. So negative 8 times 3 gives us negative 24 times x to the negative 8 minus 1 would make this negative 9. And then if I asked you to simplify, you go further. If I said do not simplify, you could leave it like that. If I asked you to simplify, this is the same as negative 24 over, remember x to the negative 9, the negative tells you to move it to the denominator, make the power positive, so it's negative 24 over x to the 9th. Don't use this negative to move around, right? The negative in front is just telling you the sign of the number. All right, so don't get that confused with the exponent rule. And then let's just take a look at a couple more. If I said to differentiate, and I said we had f of x equals negative 8x. So this one we have f of x. We're trying to find f prime of x. Well, this is a constant times a function. All right, so don't zero it out. There's a variable part in there. You can't. If it was just negative 8, right? If f of x equals negative 8, that would be like our situation up here. Derivative of a constant is 0. Here, derivative of a constant times a function, the constant stays in front, is negative 8, times the derivative of the function. What's the derivative of x? Well, derivative of x, remember, is just 1. We talked about that a little earlier in our previous example. Remember, it's like having a 1 up top, so 1 would come down, and then the x to the 0. X to the 0 is just 1, so the whole thing is just 1. Negative 8 times 1, well, that's just negative 8. So f prime of x is negative 8. And one more with this one. If I said I had y equals 1 over 3x to the 4th. First thing I want to do with this, we kind of talked about earlier, right, is I want to rewrite this because the x in the denominator, is not in the form we need to use our power rule. So I'm going to rewrite this. The rewrite sometimes trips people up. So it's still y, all right, and it's y equals, now we just need to move the x up. The 3 you can't move up. The 3 is not part of the function, it's part of the constant. So it's really a 1/3, right? You have the 1 over 3. Moving the x up to be in the numerator, make this x to the negative 4. Remember, you make the power negative to move it up from the denominator. And now we'll use our rule, right? So now, then y prime is equal to, you bring the exponent in front, so you have negative 4 times 1/3 is negative 4/3. Remember, when you multiply a whole number or an integer times a fraction, you just multiply it to the numerator, keep the denominator the same. So it's negative 4/3, and then x to the, you want to subtract 1 from the power, so negative 4 minus 1 is a negative 5. Make sure you're subtracting. And then once you have that, we have y prime equals, simplifying this. So if I said do not simplify, you could leave it there. Simplifying this, the negative 4 is still in the numerator. The 3 is still in the denominator. The x to the negative 5, the negative exponent tells you to move it to the denominator, make the 5 positive. So you end up with y prime is equal to negative 4 over 3x to the 5th. And that negative can be written right out in front of the fraction. Just make sure there's only one negative sign there. So, that's using the power rule, along with a couple other rules, right? We talked about the constant times a function. We talked about notation. And then we also talked about the derivative of a constant. So, but the important thing is when you're finding these derivatives, understanding that what you're finding is a rate of change, right? It's the instantaneous rate of change for any point, the ones we've been using, x on the function. Let's do just an applied example, just making sure that we have an understanding how that would work in an application setting. So for this example here, we'll say the volume of a tumor can be approximated by v of r equals 4/3 pi r cubed, where r represents the radius of the tumor in centimeters. All right, so they're giving you an example where the volume of a tumor can be represented by this formula, V of R instead of F of X. But keep in mind, R is like your input, is like your X. V of R is like your Y value. It says find the rate of change so find the rate of change of volume with respect to the radius. So if you're asking me to find a rate of change, what you should be thinking to yourself immediately is find the derivative, right? So we're going to look for the derivative here. So when you hear rate of change, you should be thinking find the derivative. Now, when I do this, right, you might think of it as dV over dr, right? The rate of change of volume with respect to the radius. dV over dr is really what that's saying, right? dV over dr. Or you could think of this as being v prime of r, right? Like that also means a derivative. This would be our Leibniz notation. This is more traditional notation. This kind of helps you see what they're asking though, right? The rate of change of volume with respect to the radius is dV over dr. All right, so dV dr. Now, to find the derivative, I have to start with the function. So the function I had, right, was v of r equals 4/3 pi r cubed. We're trying to find v prime of r. Well, if I'm looking for v prime, right, the derivative of this, how do you find the derivative? Well, the derivative of this, 4/3 is a constant, pi is a constant, r to the third, that's a function, right? This is the function of the variable r. So 4/3 pi, a constant in front, when you take the derivative, stays in front. And then what do? You multiply it by taking the derivative of the second part, the 3r, and then to the second power. So when you take the derivative here, right, it's still a constant times a function. I'm showing it like this just so you can see what I did, right? The constant stays in front times a function. What we did earlier is we just said bring the 3 down in front and multiply. And you could do that as well. All right, so the constant stays in front times the derivative of the function, which brings the 3 down, because 3r subtract 1 from the power is 3r squared. And then we're going to simplify this, right? So we have v prime of r is equal to, these 3's are going to cancel. So you end up with 4 pi r squared. Now, if you just brought the 3 to here and you saw 3 times 4 is 12, divided by 3 gives you 4, and then pi r, and then subtract 1 from the exponent, that's the same thing. You don't have to show the intermediate step. I just wanted to make sure you saw I was using the rule of a constant times a function. How do you take that derivative? So we have it there. Or if you wanted to write it in the Leibniz notation, dV over dr equals still 4 pi r squared. These are the same. All right, one is just Leibniz notation, one is our other traditional notation. So this gives us the rate of change at a specific radius, right? So at an instant, any instant radius, I could calculate the rate of change of the volume of the tumor with respect to the radius. Let's take a look at the follow-up to this, because that's going to help us do this next part. So if I said to find the rate of change of the tumor size when r equals 1.2 centimeters. So now they're giving us a specific condition. They're still asking us to find the rate of change, but they're saying when r equals 1.2 centimeters. So we already found the rate of change generally above. So all I need to do is find what the rate of change is at the specific time when the radius is 1.2 centimeters. So I'm subbing in 1.2 for r here. All right, so I'm really looking for v prime of 1.2. Now, if the question just asked you this from the get-go, right, from the very beginning, you would still have to do this first part. They just weren't being explicit about it. And then you still have to sub in 1.2. You don't ever sub in the 1.2 first. You always have to take the derivative first, then sub in the value they're asking about. So v prime of 1.2 is equal to, subbing in, we have 4 times pi times 1.2, the quantity squared. And, you know, you can multiply this out on your calculator. If you were to do that, we have, I don't know if you can see that so well, we'll try it. 4 pi, so this would be like an exact value if I did 4 times just that. So we want to do 4 pi times 1.2 squared, and I get, as my approximation, I'll round it to the nearest tenth. So I got 18 point, see if you can see it, 18.09555. I'm rounding the nearest tenth, so one decimal places. I'll round it up to 18.1. So this will be 18.1. Now, what are the units on this? This is something to think about. Well, remember what this was. V prime is the same as saying, right, what did we say? dv over dr. It's like the change in y over change in x. The change in v over the change in r. Well, what was v measured in? Well, v was measured in volume. Volume is measured in cubic units. So this would be centimeters cubed per, what are the units of r? Well, radius, those are measured in centimeters. So it's centimeters cubed per centimeter, which, because these units have the same base in them, you can divide this and say this is actually 18.1 centimeters cubed divided by centimeters to the first would give me centimeters squared, is another way of saying it, right? So 18.1 centimeters squared. You know, these units might give you a better idea of what's going on. These would be the actual units that you would say, right? 18.1 centimeters squared. Either way, let's talk about what this means, though, in terms of a sentence. So first off, it's a rate of change. So it's the rate of change of what? The size of the tumor in terms of volume compared to the centimeters of the radius. And it's positive. So a positive rate of change means what? Well, it means that the tumor is growing or increasing in size. So let's write a sentence just making sure we understand what we found. So this means when the radius is 1.2 centimeters, and this is important that it's at the specific point when the radius is 1.2 centimeters. If it was anything else, 1.3 centimeters, right? 0.0 or 0.9 centimeters, right? It would be a different value. But at the instant when the radius is 1.2 centimeters, the volume of the tumor, right, is, and you need to say this, growing or increasing, right? And that's because it's positive, make sure you know why, is growing at a rate of 18.1 centimeters cubed per, and this is really important, right? Centimeters cubed per what? This per centimeter means per every 1 centimeter change in radius. So per 1 centimeter change in radius. And that's why I said this, you know, this first answer gives us the units we kind of want to work with, because it's giving us information. It's saying that, first off, you know, growing because it's positive. You have to acknowledge if this is positive or negative by saying it's either increasing or decreasing, or, you know, growing or shrinking in this circumstance. But the centimeters cubed per centimeter, it's telling you the change in volume, right, per every 1 unit change in this case, centimeter of the radius. But understanding that when you find an answer like this, it's always per every 1 unit change of whatever was in the denominator. So the radius, when the radius is 1.2 centimeters, at that instant, right, derivatives are the instantaneous rate of change at a point. The volume of the tumor is growing at a rate of 18.1 centimeters cubed per 1 centimeter change in the radius. So just looking at the application using derivatives. I think it's helpful to see that. So hopefully this video helps. We're going to be going forward looking at a variety of different derivative rules. And the applications we'll do throughout the course. So once we do some rules, we'll do some more applications, and we'll go back and forth between the two.